Hi everyone, welcome to today's topic. This is my topic number 6. It is based on carbene. The carbene is a special type of reaction intermediate and it is obviously from organic chemistry. So in this lecture, you will know about carbene, what is a carbene and what is the type of carbenes we can see during a reaction and what kind of reaction it will give and it will show and in which manner or by which process carbene actually form. This kind of things are there, and obviously some PYQs are also incorporated in this video lecture. So let's start with this topic. So carbene. So why carbene is important? So after seeing a topic, some questions you should come in your mind, that what is it and why this is important, why we are reading it, right? So uh, why we are reading is that the question can be answered by simple, just a simple one line answer can be, what is this? I have previously told that it is a type of reaction intermediate. So we know that chemistry is all about reactions, right? And reaction intermediates are important to explain a reaction or explain the product formation. Okay, we know that this and this, if we mix, and this will be the product, but how the product is forming, how we can predict some product by seeing reactant and its conditions. Okay, that is our main concern. So that's why the reaction mechanism, the intermediates, that's why these are so much important. But to study the reaction intermediates, sometimes not, most of the times it is found to be difficult because we can't isolate the intermediates, as these are short-lived and very much unstable. Okay, very reactive. So so scientists have done some research, and we could know about the carbene intermediate. So we know the carbocation, carboanion, radical. These are some common names we know. Many of you are very much actually familiar with these kind of names and their properties. But what is carbene? Carbene is a very important intermediate. We should know about it to know organic chemistry more. And for CSIR NET exam, actually, various type of questions which are actually asked by which can be explained or which can be tackled by the carbene formation. Okay, so let's start with the topic. So what is carbene actually? So carbene is a unstable, by definition, it is a unstable, electron deficient, neutral, carbon based intermediate which has two bond pairs and two unpaired electrons. Okay. So what is the structure? We can represent carbene like this way. It has two bond pairs, you can see, and two unpaired electrons. So by definition, we know that this is carbene, but we should know about this kind of properties, right? So, unstable. Okay. First, electron deficient, question mark. How we can prove that carbene is electron deficient? So, to know about this, we are going to again the structure. So, two bond pairs means here two electron, and here two electrons are there. So 2 plus 2 is 6 electron. And we know that to have a stable structure, or every electron is prone to or intend to have a noble gas like structure. So 8 electron it should have, right? So you must be thinking that carbon has also 6 electron. It is stable, but it is not stable like the inert gases. So it has, every molecule has a tendency to fulfill its octet. Okay. So it is a electron deficient species. So tick that it is proved. Next, unstable. Yes, of course, I have told you that it is an intermediate, and intermediates are actually formed during a reaction. So during a reaction it is formed and it is again it again reacts to form product. Okay, so it is obviously unstable. Obviously. Neutral, question mark. So this is important, right? Because for carbocation we know it has positive charge, right? For carboanion we know it has negative charge. But here in this case, if you see that it has an electron deficiency. Electron deficient and charge is different thing. Electron deficient, how we can tell that it has 6 electron, so it wants to gain 2 electron more. But is it uh, we can we say it as positively charged? No, right? Because it is electron deficient, but it doesn't have any charge on it, so it is neutral. Please remember it. Neutral intermediates, carbenes and radical. Okay. Next, examples: CH2 radical, CCl2 radical, CHPH. This is like this: CH and PH, two unpaired electrons, right? So if let's say if I can give you a simple overview of the formation, it should be like the if this bond actually breaks and this bond also breaks, then this kind of carbenes actually form. We will come to again the formation of carbene part. Let's see now the types of carbene. Okay, there are two types: singlet carbene, triplet carbene. Okay, so there is a reason why it is named like that, singlet and triplet. Okay, so first the structure, right? So we know that it has two bond pairs and two unpaired electrons. But two unpaired electrons can be in same hybridized orbital with pairing. So this is wrong. We should not write two unpaired electrons. We can write it has maybe two electrons. Unpaired we can't write it. Okay. So it is actually the sp2 hybridized carbon. So carbon has, we know, 2s and 2p. 2s2, 2p2, right? This is p, 2p. This is 2s. So 2s2, 2p2, carbon. This is for carbon. Okay. So this is the p orbital, this is s orbital. So when singlet carbenes are actually formed, that time this will be like that only, and hydrogen will be attached to it. Okay. But for the triplet case, what is happening is there is, and so it will be jumped through this. So in the excited step, like this way it form. So all are actually sp2 hybridized, right? So one p will be only there. It can be px, py or pz. Let's say it is px, and these are sp2 hybridized orbital, and these are sp2 hybridized orbital. So what difference you can see here? Here these two will form bond. Let's say this one, these two sp2 hybridized orbital. So here one sp2 hybrid orbital has one electron, and one p orbital has one electron. Okay, but here one orbital is vacant, empty p orbital is there, and in the sp2 hybrid orbital one lone pair present. Okay, so structurally if you see that both has two bond pairs, one lone pair. Lone pair we can't say. Let's say two electrons. But how their electrons are there? So in one case for the singlet carbon, here what is happening is that in one sp2 hybridized orbital, the lone pair is present. But for the case of triplet carbon, in one the electrons are divided into the sp2 hybridized orbital and one px orbital. Okay, so both are sp2 hybridized orbital. This is also and this is also sp2 hybridized carbon, right? So this is the thing, and here one empty p orbitals are present. Orbital is present. Here no empty p orbital is present. Hope you understood this, right? So when we see differences, then you will understand it in a easy manner. Okay. So singlet and triplet carbon. So the differences I have incorporated. So first one is it has two bond pair and one lone pair. Lone pair, okay. It's one paired electron we can say. Paired electrons. Okay. I am not saying this is lone pair, okay, but because this is different than the oxygen and nitrogen lone pair, this kind of thing. So let's not talk about this much. So triplet carbon, it has two bond pairs and two unpaired electrons, correct? We know here the image also I have incorporated here so that you can relate it. Okay, so here one point can be there, that here one empty p orbital present, here no empty p orbital is present. Okay, next it is diamagnetic as it has no unpaired electron, but it has unpaired electrons, right? So it is paramagnetic. It is also proved. ESR inactive because ESR in the case of paramagnetic case it will be ESR active. So it is also correct. Angle is less than expected. Why it is so? It is almost 103, but we know that for sp2 actually angles is varying between like 120 is expected. Expected means it is not expected, theoretical value is 120, but it is less than that, 103. But here angle is more, it lies between 130 to 150 degree. So sometimes in many books they are claiming that it is sp hybridized. So you can write in both ways. Both will be correct, I hope, because in many places the singlet carbene is the carbon of singlet carbene is written as sp2 hybridized and triplet is sp hybridized. But I am following the Clayden book, so they have explained it in two manners. Both are actually there. So if you write like sp2, it will be also fine. Okay. So angle is like lies in this, and it has bend structure, and it is more or less almost linear. Okay. And why it is singlet and triplet? The names are actually coming from the spin state. Okay. 2s plus 1. So we know spin multiplicity equal to mod 2s plus 1. Okay. S is the total spin of electrons. Let's say for singlet. So this is plus half, let's say. This is minus half. Okay. You can take the opposite also, but one will be plus half, one will be minus half. So total spin will be plus half minus half will be 0. So S equal to 0 for singlet carbene, where one empty p orbital present and electrons are paired, right? So 2 into 0 plus 1, it will be 1. when the spin multiplicity is 1, then we can called it as singlet state, and in the case of carbene it will be called singlet carbene. Like the same way here S will be, if it is plus half, here we have told you plus half, so plus half and plus half, it will be 1, right? So if we put value 1 here, it will be 3. When spin multiplicity is 3, we called it triplet step. So in the case of carbene, it will be triplet carbene, right? So for example of the singlet carbene is, some examples I have incorporated. So it is, so electrons are present here, this, okay, CH2, CHP, CHR, and examples of triplet carbenes are CCl2 dot dot, CF2 dot dot, COMe dot dot. If you see here, by seeing these examples, you can see here when some electron donating group is present with the carbene carbon, that time triplet state. No, 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 no. Really sorry. So examples are actually, this is exchanged. Example will be this one. Okay. So examples of singlet carbene will be, I hope you are not confused. Example of singlet carbene will be CCl2, CBr2, CF2, etc. Okay. And examples of triplet carbon will be CH2, CR2, R can be any alkyl group, and CHPH, etc. Okay, now clear? Now it is fine. I have cut it down. Okay. So if you see, for the case of singlet carbene, it is forming when one heteroatom present, one electron donating group, or any atom has the electron lone pair with it. That time singlet carbene actually form. So I'll come to the stability of the carbene. In that part you will understand it in a better way, but see the differences when you are actually you want to remember the, it will be helpful also the remembering of these examples, because sometimes it will be not written like that it is singlet or triplet. Okay, so you have to consider it from your knowledge. So when heteroatom present like Cl, Br, F, O, the atoms having lone pair in it, that time singlet carbene forms. And in the case of other like alkyl, H2, PH, in that cases the triplet carbene forms. Okay, the reason we will know in later parts. So next, some important points. Okay, most type of carbenes are more stable as triplets. So here we are not saying that triplets has more stability than singlet in every cases. No, they are saying that most type of carbenes are more stable as triplets. So in most of the cases, triplet state are more stable. Okay, and the reason is the energy to be gained by bringing the electrons in the p orbital down into the sp2 orbital is insufficient to overcome the repulsion that exists in between two electrons in a single orbital. So in the case of singlet, we have seen that this is paired. So when it is paired, so from unpaired to pair, going to paired state, it will be some energy uh, should be actually given. Okay, because here electron when pairing happens, electron repulsion will be there. So to overcome, okay, so when these the electrons are in the p orbital, it has high energy, and sp2 orbital has little less energy. So we know that when we are coming from high energy to low energy, it is favorable because it will be more stable. When energy profile diagram, if you think about, so let's say this is energy. Okay, energy. So it is a higher state, excited state, we are going to less energy state which is stable, like it is let's say this is sp2, okay, so this will be stabilized there, right? But it is not favorable. Why? Because it is not sufficient. The energy gain, the stability gained by the movement from here to here, it is not sufficient as the repulsion to overcome the repulsion between these two electrons. Okay, so two factors are there. When they are coming to this state, energy is released, so minus E1, let's say minus, and plus E2 is there where repulsion exists. So there should be the some stabilizing factor, because in most of the cases they are saying that delta E1 is less than delta E2. The effect of delta E1 is less, the stability or stabilization is less than the repulsion. So repulsion is more, so some extra stability factor should be there, right? So most of the cases triplet is stable. Okay, so the reason is this only. Understood? Now stability of carbene. Okay, triplet CH2. So two factors, two examples we will take and explain. Okay, triplet CH2 is more stable than singlet one. Okay, so we have taken here triplet. Triplet means the electron will be in one sp2 and one p, like this way. Okay, and if it is singlet, then this will be paired in sp2 and this will be vacant. Fine. So why here it is saying that triplet CH2 is more stable than singlet. It is the stability of this one is more, because the same reason which we have studied right now, just now, that to pair up the electrons, to pair up, let's say this is p orbital, I am again telling you, and it is sp2 orbital. Okay, so p orbital has two unpaired electrons. If it comes to here and pair up, so it will be stabilized. The stability factor, some stability factor is there. Let's say this is delta E1, but here for due to repulsion there is one factor delta E2. Okay, so here repulsion factor is more than delta E1 stability factor. So some extra stability should be needed for the triplet state, singlet state to be stabilized. So here for the normal cases, what is happening? The triplet CH2 triplet state will be more stable. Okay, hope you understood it. And next one is singlet CCl2 is more stable than triplet one. Here this is different. Singlet CCl2 is more stable. So we have previously read it, right? When C is attached with any heteroatom or halogen which has lone pair in it, okay, that time that carbene is stable. Why? Okay, let's say this one, this is singlet, this is vacant, and this is, let's say, triplet. Let's not talk about this now. This is triplet. Okay, let's see here. So as it is vacant, here one vacant p orbital presents. Vacant p means like this. Okay, and it has also lone pairs in p orbital. It has lone pairs in p orbital and it is vacant. So these electrons these electrons are actually go to this one, this empty. So here what I was telling you, that some extra stability factor should be there for a singlet carbene to stabilize. So here is the extra stability factor. It is stabilized by the back bonding of p orbital. So this is p pi overlap, p pi overlap, and from 3p. So it is 3p to p overlap. 3p to p overlap. Okay. So this is the extra stability factor here. So here the singlet CCl2 will be more stable than triplet. Hope you understood this. So whenever you are asked that some carbene is singlet or not, or triplet or not, just keep this in mind, because this trick actually I am also using for remembering this example. That's why I have just correct the I could correct the slide, the examples of the previous slide, because I have seen that in the case of singlet there is vacant orbital. Singlet means they are paired up, so is equal to 0, and field multiplicity is 1. Clear? So what can be the stability factor there? How it is stabilized? Here vacant orbital present. Oh, in the vacant orbital, someone can give electrons, right? So if there is one heteroatom, then that time singlet carbon will be the more stable form there. Okay. Now, question. Compare the stability of CF2, CCl2, CBr2. Here it is not written that it is singlet carbon, triplet carbon, anything is not written. But what you have studied till now, that whenever a heteroatom present within the carbene carbon, this can actually donate its electron to empty p orbital of singlet carbon. Back bonding it is called. Okay. So this is, we are considering it as singlet. Fine. So it will all having lone pair. So it can happen with all. Right? The back bonding can happen with can happen in the case of all actually. Okay. But okay, I'm not drawing again. Drawing for these cases. So here it is 2p overlap, because here halogen atoms are present, it has lone pair, it can donate. Clear? But only you have to find any differentiator. How can we differentiate? We know that fluorine is less in size. Okay, size factor is fine, but we have to say it more specifically. The here it is overlap, so orbital matching is important. Size matching or orbital matching is important for a overlap. So it is 2p, we know it is also 2p, but here 2p 3p, this is 3p fluorine, and here 2p 4p. So we know that for a better overlap, size matching or the same kind of size of orbitals actually overlap in a better way, not like this 4p and 2p is like this. So overlap is not good. So best overlap will be for 2p 2p case. So the stability order will be clear, right? Clear to you right now? You must have written the answer. This will be the stability order. Next, formation of carbene. This is very important because it is an intermediate, so it will be formed in inside the reaction. So we have to have some idea that how it can form, because in the questions there are some parts in CSIR NET specifically, they are not asked you one reaction. They are given they are actually giving multiple reactions in a series of manner, right? In a series manner. So maybe some reagent they will give which is actually helping to form a carbene, and after that, after the formation part, we will know about the reaction, and also I will make another video of the reaction of carbene intermediates or reactions which involve actually carbene intermediate, that I will again told you. So for that reaction, okay, so if you know the reactions of carbene, in the first portion it is given some components or some reagents are given which can form carbene, and next in the next step it is given some another reagent which will be the part of the reaction of carbene. So You have to have the idea of the formation as well as the reaction to attempt one question. So that's why organic is a bit difficult, I will say, because you have to have the idea of various reactions and various ways of reaction mechanism, everything you have to keep in mind. Because in one question they can be asked, the question can have the content from like 3-4 chapters or more. Okay, so be aware of that. Now coming to the formation of carbene. Okay, so this is from alpha elimination reaction. So what is alpha elimination? When from one let's say carbon, we know it can form bond, four bond it can form. So by alpha elimination means with from one carbon, two bond will be broken down. So it is actually alpha elimination. Okay, when two bonds are breaking in from one carbon, okay, from the same carbon atom. So what will happen here? So here CH, Cl, 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 right? Here KH is given. So base will first abstract the proton, right? Because it is more easier. So it will abstract proton, and this will be the here negative charge will be in the carbon atom. Carbon, not it is carbene right now. Right? Here it is. And then once if one Cl atom leaves from this intermediate, Carbanian intermediate, then CCl, Cl, carbene will form. Okay, so here one bond breaks, and in the next step another bond breaks from the same carbon. So it is alpha elimination. When it will undergo, when base is present and one hydrogen is there, it will abstract hydrogen first, and then if any good leaving group present in the carbon atom, it will leave. Okay, here minus here. Here K is present, K plus, so it will be obviously Kc. Right? So here also the same thing, but here CH, F, F, Cl. So two F are present. First, there will be abstraction of proton. So the intermediate will be F, F, Cl. So now the question is, which element will leave? Which group is leave? Is it the Cl or fluorine? So we know that fluorine is less in size, right? And CF bond will be more stronger than CCl. So it will leave actually. So minus Cl will be there, Cl minus, and CF2 carbene will form. It is singlet or triplet. This both of these heteroatom present means singlet, right? I'm again and again telling you so that you have a clear idea. Okay. Here is also the same thing. Here I2 is given. So in the second step, one I minus will leave. So the product will be one I is there and another Br will be there. Br. So it has this carbon will form. Okay. Now one reaction also I found in Clayden, so that I have incorporated. So Cl here heating is condition is given, and one here carboxylate group present. So CO2 elimination will happen. So CO2 elimination, when it will happen? So every time when acetate is there, acetate group is there, and right, acetate group is there, and it is given that heating condition. So every time the CO2 will leave? No. Why? CO2 will leave when this carbanion, which is formed after CO2, after the leaving of CO2, that will be stable. When this carbanion will be stable, this carbanion, this one. that time CO2 will leave. So here it is stable. Why? These all are halogen groups. This has a high electron withdrawing capacity. So carbanion will be stable. This negative charge will be drawn by 3Cl group. Next step, in the next step, what will happen is that Cl leaves like the same way, here in the like the second step of this one. Okay, this is also a alpha elimination. If you see here, one bond breaks from this carbon and another bond breaks also from this carbon. Okay, this is also a kind of alpha elimination. So now from diazo compounds. Okay, so from diazo, what is a diazo compound? When these kind of groups are present, this is actually diazo group. So here CH2N2, for the case of CH2N2, what is the structure? So structure can be many because it is a resonating structure, but this is here also it can happen like this. Many structure is possible actually in triple bond N and positive. Okay, so this is called actually the diazo compound. When any pyrolysis or photolysis means heating condition or H nu is given, that time the N2 will leave here, from here. If you see here, N2 will leave and form CH2 carbene, right? This is the thing here. Here also, okay, some metal, any condition or heating or H nu or metal present, that time if this kind of diazo group you can find in any compound, that time here rhodium present, so carbene will form. Okay, this kind of rhodium carbene complex is formed by this carbene is stabilized, because we know that it is not unstable, right? So here what is happening from tosyl hydrazone. Okay, so here what is happening, first TSNH2. Okay, tosyl hydrazine is given with NaOMe. This is a base. So first it will go like this one. NH2 is there, na? NH2. So water will leave, and here N NHTS. Okay, so it will make a bond here, and now this is called tosyl hydrazone. Okay, and OMe is there, so it will abstract one proton from NH, and this negative charge will be there, and here lone pair present, so it will be there, and this is actually a good living group, tosyl group. Okay, so tosyl group will live, and then this kind of structure we can see. Now if we think about this resonating structure, it will be like this, na, diazo compound. Okay, this will now form as like diazo compound. So here pH negative and N2 plus is there. So if now N2 will leave, then this kind of carbene is formed, right? Right? So now reactions of carbene. Okay. Reactions with alkene. First we will see reaction with alkene. So it is not formation, it is reaction. So reaction with alkenes. So when alkenes are actually present and CCl3 and KOH, we know it will give CCl2 dot dot. As it is intermediate, these kind of conditions are given only in the reactions. So it will make carbene and react with the alkene. Okay, this kind of formation is there. So if we see the mechanism, it is a concerted manner. Okay, so it will like this and this. Okay, so this kind of product will form. So seeing the mechanism, you must be thinking that it should be stereo specific, right? Concerted manner the reaction is happening. So let's see for the case of singlet carbene, because both are giving actually different products. So that's why I have pointed out reaction with singlet carbene. Singlet means singlet again. C, okay, okay. In sp2 orbital one lone pair present and it is vacant. Remember, this is singlet. Okay. So for the case of singlet carbene, and we know that when heteroatom present, it is singlet carbene. Okay. So it will be stereospecific reaction. What it is it means if we are starting with trans, that time in the product when the cyclopropane ring actually form, that will be also trans, right? When it is cis, the alkene is cis, that time the product will be also cis. Means the reaction is stereospecific, specific for a product formation. Okay? Of a product formation of a particular stereochemistry. That's why stereo specific. Next, reaction with triplet carbene. In the triplet carbene, let's think about the structure and the arrangement of the electrons. Okay, in the p orbital and sp2, one electron is here, one electron is here, right? So no vacant orbitals present, and the electron spins are like same way. If one has positive half plus half, other one will be also plus half, right? So reaction with triplet carbene. Let's say this is a triplet carbene CX2 and this alkene we have taken. So as the both electrons are different spin, not different, same spin, that's why reaction will be stepwise. Because if we break the double bond for a bond formation, we know that, so we know that one will be up spin, one will be down spin. Here, one will be up spin, one will be down spin. So if it has all up spin, so this up spin and down spin can form a bond, right? But this up spin and this up spin cannot form a bond. So that's why it is stepwise manner it will form. But here it was, here in this case, it was like this one. I am telling you. If let's say I am taking C's, so if I break the double bond and just for your understanding purpose, so we know that this is one will be up, one other will be down, right? And the carbene also has a electron pair which has one up spin, sorry, one up spin and another down spin. So this down spin will join with up spin, and this down spin will join with up spin. Okay, that's how the in concerted manner the bonds are formed here. Clear? But here this is not the case. So here here in this state, what is there is here up and up present. Up another up is formed bond with one down, but here up present, so it is triplet intermediate, right? Here spin inversion is necessary to form a bond between this C and this C. Spin inversion is here necessary, so spin inversion happens, but it is a slow process. Just remember, it is a slow process. So after spin inversion, actually this is formed product. Okay, but how we can explain this stereoselective? One important thing is there before when the spin inversion is happening, as it is a slow process. Here in this step only the bond can rotate, as it is a single bond, it can rotate, right? So if bond rotation happens here, so here they have not I have not actually tell about stereochemistry, just for the general way I have shown you. But if stereochemistry is mentioned, like if let's say this is cis, so cis will be the stereochemistry here also in this intermediate. But whenever a spin inversion is going on, if this bond rotates, it will be then trans, and spin is up again, and it will be trans. So both are possible here, 1 and 2. So here in the triplet intermediate, it is mixture of 1 and 2, and then it will give spin inversion like this way. So both in the both cases spin inversion product like single intermediate with having also the 1 plus 2. Okay, both are actually possible here. I have not shown to you, but let's imagine that the spin is inverted and these both stereochemistry present. These both product will be present. So let's say 1 dot, 2 dot will be present after spin inversion, and then when product is formed, these two products are actually possible. If you see here after the spin inversion, it will be like this, and this will form bond. This will be the product, and it is also possible. So why it is stereoselective? Because here spin inversion, for the case of triplet carbene, spin inversion is necessary for the reaction with alkenes. And whenever the spin inversion is going on, the bond which is now a single bond, it can rotate and the stereochemistry can be changed here. So this both product actually formed in a larger amount. So there will be some ratio, but two products we can get. So these kind of reactions are called stereoselective. Selectively, one will be major and other will be minor. So this will actually depend on the reaction conditions and all, but there will be two ratio. So a major and minor will be there, but two products will be formed. The second kind of reaction of carbene is that insertion into CH bonds. How it happens actually? So let's say this kind of structure is given, this HH is present there like this, and Cl is present. H, let's say. So and K is given and it will abstract one H and again Cl. So it will give carbene. And if anything is not there, that time carbene is very unstable, you know, but here no alkene and nothing is given. That time what it can give? It can give alkene by CH insert. CH bond will be inserted here and carbene electron will be here. So see, H is gone to this carbon. So CH insertion, this H. If it is let's say 1, this 1H is this one. Okay, so it is an example of CH insertion. When carbene is formed and nothing is given in the reaction condition for further reaction, that time we can think about this one. Okay, because carbene is unstable. And in the next example also, it is a bigger example where ring formation is there. So this is diazo compound. We know when any metal, heating condition or H nu is present, that time diazo compound give carbene. Carbene is formed. Okay. So now here hydrogen is present. So if it forms a bond, then if hydrogen is there and lone pair will be there, so these two actually CC bond will form and 1, 2, 3, 4, 5 member bond will form. So this has 60%. This is also an example of CH bond insertion. Now coming to the question part. So in this session actually not much questions I have incorporated because the reactions are actually much left. Many reactions of carbene are actually there. So I want to teach you that, and after that I will incorporate various questions from CSIR NET as well as GATE also, because GATE questions are also important for CSIR NET. Okay, so let's think about this. This is CSIR NET December 2013 question. So in this following reaction, the intermediate and major product will be. So there are 4 options are given. So we know CaCl3 is given, KOH is given. So intermediate will be CCl2, this carbene, right? And how actually, so you are not heterocyclic chemistry. If you know about this, I will try to teach you that also. But if you don't know, just think that, see here that this is benzene will not attack, and this ring, the attack will happen from this ring, and it has more electron, it is more electron rich for the nitrogen. Okay, so lone pair will be here and it will go to here. Okay, like the alkene insertion. Only confusion you must have that there are various double bonds present which will attack. That can be your question. So you will know about this when you read about cyclic chemistry. But for now, if we can see that benzene is all having carbons and here are nitrogen present, which is is a electron donating group. So that's why it will attack and form CCl2. This will form ClCl. This is a triplet carbon stereospecific reaction. So it will form like this. Cl and Cl. Okay, two Mes are present here and other things here on double bond and positive charge. Okay, so what will happen now? Is it stable like this way? No. In any options you can't see that this option is there. So now what happens? Let's say we have neutralized the nitrogen. Here positive charge is there and so clear. Now what is happening is that here okay here actually no the lone pair will not move. So this is electron rich this is electron rich ring. So that's why it will attack. This is fine. But here this step will be not there because if you see here four bond will form already. So there is nothing to do with this lone pair because in this you can see here I will okay. So here if you see four bonds are actually there. So the lone pair has nothing to do uh, the delocalization is not needed here. Let's say Me. Okay, Me is there. Me. Okay. So 1, 2, 3, 4, 1, 2, 3, 4. 4 bond is there, na? So now this lone pair will attack here, go to here, and then this bond will move towards this one. Cl will be removed. Okay, one Cl minus will be removed, and this is benzene ring, right? So now it will form benzene. This will now six-membered ring. Nitrogen is present. This will be the positivity sign is there. Positive sign is there, and one another double bond present here. Me group is here. If you see, Cl is here. Okay. So here hydrogen was there, and if we want to neutralize it, then hydrogen will be removed. Okay. So what will be the answer? Tell me. One Me is there. Okay. So if you confused about the where the group will come and like that, so you can numbering. You can put numbering 1, 2, 3, 4, 5, 6. Okay. So see this will be six member because it is broken. Okay. So 5, 6 if we put here because it is not changing. Okay. So it is 1, 1, 5, 6 I have put 2, 3, 4. So 4 had Me group, 3 has Cl group, and 2 has Me group. Okay, like that way you can think of it, right? So answer will be the CCl2. This question is actually wrong. C2. Question is actually wrong. So I have to see. This will be answer. You see here. Okay. But it is alpha elimination, right? This is alpha elimination, and if presence of this is here. So what will be? It is first abstract the proton, obviously. So this will be the answer, but this is not correct. Okay, I have to see the options, but this is there. If you see, so this will be the answer. Okay, fine. And CHC2. Okay, here it is wrong, I think. CHCCl2 will be there, and this will be there. This product. Okay, I hope you understood this. Next, so the product of the following reaction gives 6 line in C13 NMR spectrum of this. The structure of the product is, and the reaction is given H nu and NaOH. So you must be thinking that why C13 NMR product is given here, because we are reading carbene, right? But if you see the reaction, this is not necessary. You can check it later after the formation of the product, but it is not necessary here. Why? If you see, if I draw the structure, it is like this one. This is diazo, and H nu is given. Let's forget about MEOH. First, it will form carbene, CO, and carbene. Okay. So after the formation of carbene, what will happen is here one rearrangement will form, and this will go to this carbene, and this will go to this. So CC insertion will be there. Like that way, or rearrangement you will say. Okay, so here only one bond can be present. This and this. Okay, so this will be this and this. So C double bond O will form. This is called, this kind of intermediate is called ketene. Ketene. Okay, so how, if you are confused, let's think about this. 1, 2, 3, 4. So 1, 4 are constant here. 1, 4, and 2 is this one. Okay, 2 is this one, right? And 2 is going here, so it will be double bonded, and 4 is attaching here, so 4 is attaching with 2. This is fine, and this will be 3. Fine, is not difficult. Now it is also not stable. The ketene is also not stable here. So in the ring you can see this is 1, 2, 3 sp2, so it is not stable. So ketene will again react with MEOH. MEOH will attack here. It will go towards this, and it will come again to this, and it will go to this. So the product will be the here. Okay, this will go to this, and this is attaching here. COOM. This will be the product. If you are confused, you can see one step. Okay, I will show you here one step. Like this way. Okay. This one, and the COMe has attacked, and this is O minus, and this is double bond. Now this will go to this one, and this will go to this one. And MEOH, so H plus is present, not H plus. From MEOH actually protonation will happen, and this will go to this. So the product will be obviously C. So you know the structure, right? You don't have to remember the C13 NMR spectrum here. So if you know about this one, you can easily solve the question. So in the C13 NMR, actually, you have to count how much carbons are actually present. So it says that 1, 2, 3, 4, 5, 6. 6 type of carbons are actually present. So in the product here, if you see in the product, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are actually same. So and this one and this one. So if you cut it, so it will be 1. This is same, so we will count as 1. This and this will be also same, we will count as 1, like total 2. This is 3, this will be 4, this will be 5, this will be 6. I hope you understood this. Okay, so in the C13 NMR, actually we have to kind of count that how many different kind of C atoms are present. So that I have done, because one plane is present here in this structure. This structure also, let's say one plane is actually cut here, so these two carbon will be same, these two carbon will be same. The plane is come in between this one. Okay, so this is the thing. So I will stop here, and again I will show you in the next class the reactions of carbene. Okay, so hope you will enjoy this session, and please read about the types of carbene and the other things here which I have taught about. And the questions also, the questions are actually based on mainly the reaction, and within the reaction the conditions, some conditions are given which will form the carbene. So I will again talk about this. So for now, thank you so much for listening.